All right. Hey, so the question is, what does it? What first question should be, what does this mean? And again, if you take calculus, and I hope you do, you'll make this a lot more precise. But for right now, what it means is, can we say anything about what happens to this formula when n becomes arbitrarily large? Just make n larger and larger and larger and larger. Okay. So let's see if we can say anything about that. I've written that formula down twice. I guess I don't need it twice. Once is good enough. And you remember, oh, just as a review, let's review what this meant. That this S sub n, this meant, um, here's where things can get a little bit tricky. Because we can start this series either with r raised to the power of 1, or we could start it with r raised to the power of 0. And that's going to result in a slightly different value for this formula. Now, I actually forgot which one I did, so hey, this is a perfect time. Do a little review. Let's say we start here like this, plus, that marker's no good anymore. Okay, plus this, plus dot, 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 plus r to the n. And remember the trick, if you forget the formula, the trick is to multiply both sides by r. So you get r s sub n equals r to the power of 1. We're multiplying both sides by r. So if you multiply this by r, rules of exponents, so on and so forth. I guess I already covered that. So r squared plus r cubed plus da, 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 plus r to the n plus r to the n plus 1. And that's what you, this term here is what you get when you multiply this term by r. And then we subtract, this equals this, so we subtract this from this side and this from this side. And we wind up with this, s sub n minus r s sub n equals, almost everything cancels out here, but we get r sub 0 minus r to the n plus 1. I'm going fast because I already did this. Right? So, and then let's factor out the s sub n and divide by what's left over, 1 minus r. So you get s sub n equals r raised to the power of 0, which is 1, right? So let's go ahead and maybe write that down as a 1. Anything to the power of 0 is 1, remember, always. At all times, r to the n plus 1 divided by 1 minus r. Okay, now notice that's not what I had up here. And so what that tells me, or at least suggests, is that last time I started with just r. They're two different cases. They're trivially different. I mean, it doesn't really matter. You know, frankly, when you do this, you're just saying, oh, add 1 to it. We can use either formula to do the things that we want to do. We can use either formula to do the things that we want to do. Let's use this formula. I was going to tell you why, but how about let's just say I want to use this formula right here, and maybe I'll tell you why in just a minute. Okay. So let's see, where are we? Let me erase everything we don't need. Erase, 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 erase. So it's going to look like I'm doing a very bizarre thing here, but I'm going to put a 1 in there. And what that means is, see if we can remember, we're starting with 1. We're starting with r to the 0. So this formula, I mean, we can make a little note over here. Note, s sub n equals r to the 0 plus r to the 1 plus r to the n. So I don't forget that now. And our interest now is to add, what we're interested in is to ask ourselves, what happens when n, the terminology is when n goes to infinity, and what we're really saying is when n grows without bound. Can we say, well, there is some terminology surrounding this, but is there anything we could say? Is there any are there any patterns that we notice? Well, imagine n goes to infinity. So if you like, forget infinity, just make n a million, make n a billion. How about this? Make n a googolplex. Well, let's go back to, how about just a trillion? Make n a trillion. And just for fun, let's say r is equal to 1/2. That was a good starting point in that score that I drew in a previous video. That would set r equal to 1/2. So it's a good place to start. What can we say about this? As a matter of fact, here, let's go ahead and just write down n sub a million, so 10 to the power of 6. 1 is 1, that doesn't change. Let's just look down here. 1 doesn't change, r doesn't change. So in this case, r is 1/2. So let's write down 1 minus 1/2, and we can calculate that when the time comes. The action is right here, minus 1/2 raised to the power of, that would be 1,000,000 plus 1. I mean, the plus 1 hardly matters here. It might not be a bad idea right now if you got out a calculator and you did the following thing. Or just think of this in your head. What's 1/2 to the power of 1? 1. What's 1/2 squared? 1/4. 1/2 to the power of 3? 1/8. 1/2 to the power of 4? 1/16. 1/32, 1/64, 1 over 128, 1 over 256. Try typing in 1/2 raised to the power, just do to the power of 1,000,000, and see what your calculator says. So pause, give it a try, or anticipate. Oh, excuse me. You should try to anticipate in advance what your calculator is going to do. Now try it. What did you get? Surprisingly, you probably got 0. Now think about it. It can't be 0. It can't be. Any non-zero number raised to a power, there's no way it could be 0. But what's going on is it's so close to 0 that when your calculator does its internal rounding off, it rounds off to 0. Now with modern calculators, you can imagine that's got to be unbelievably close to 0. In fact, what you get is, 1/2 raised to the power of 1,000,000 is 1 over 2 raised to the power of 1,000,000. Now 2 raised to the power of 1,000,000 is an unfathomably large number. I don't really know a particular way to contemplate that number. I mean, the total number of atoms in the universe. If my memory serves, is maybe, I'm going to be off by a couple orders of magnitude. You can check this out, but 10 to the 90th. So let's go crazy and call it 10 to 100. This is a much bigger number than that. So this is 1 divided by a number larger than all the number of atoms in the entire universe, or observable universe. So 1 divided by a number that large, it's not 0, but you might say for all intents and purposes it's 0. So after all that, what can we say? We can say that, or we're going to say that this is equal to 1 minus 0 divided by 1 minus 1/2. Now, I left the 1/2, I left this uncalculated down here, and the reason is, well, let's just get right to it. If r is less than 1, or in particular between 0 and 1, any number between 0 and 1, when you start raising it to higher and higher powers, the value gets lower and lower and lower. Now you can do a little experimentation with your calculators. Pick a number between 0 and 1, any number, 1/2, but 1/3, 1/4, 0.9, 0.9782, 0.3459, whatever you want, doesn't matter. Take a fraction or decimal and take a number between 0 and 1, and then raise it to powers higher and higher and higher, and you'll see that it gets closer and closer to 0. And the idea is, if we sort of thought of ourselves as making that number infinite, it really would be 0. So after all that, now what we can actually say is the following. We get a new formula, and the formula looks like this. This becomes 0. And this is for r is, for right now, for our purposes here in Math 96, I'm going to do something, and maybe we can make this more general, but for right now, let's just consider the following. This applies only when r is between 0 and 1. If r is 1, well, think about if r is 1, we run into trouble down here, so we have to put the brakes on right away. 1 minus 1 is 0, we can't divide by 0. If r is greater than 1, then this just grows to infinity. This number gets larger and larger and larger, and we can't really say anything about that, or maybe we can, maybe we can't, who knows, we'll leave it for another day, but we don't want to play that game right now. So in negative numbers, I'm just going to stay away from those for right now, in particular because they can add complications. But particularly for those who get to second semester calculus, you'll have to go back and deal with a lot of these things. But this formula right here This is a formula that we want, and that is important, and has affected you in your actual lives in a way that we'll see in the next video. Oh, it's so tempting to do this right now. You know what? I'm gonna do something right now because I can't resist. I need this formula right here. Your whole lives, or maybe not your whole lives, but for a long time now, you felt probably comfortable. You probably felt comfortable writing that down. Or maybe you felt comfortable writing down pi is 3.141, blah, 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 or the square root of 2 is 1.414. I don't know. You can go back and calculate it out. But what does this mean? What does this even mean? I mean, I was taught this in 7th grade. And I certainly didn't ask this question, but if I could go back in time and be in 7th grade again, I would. What do you mean these threes go out to infinity, or that there's an infinite number of these threes? Like, that needs some explaining, because I've never seen an infinite number of anything. Maybe in my mind's eye, but let's say in the real physical world. And certainly, I think as a 7th grader, if you would ask me to show you an infinite number of anything, I think I would be at an extreme loss to do that, particularly in 7th grade. So what does this mean? And now we're actually in a position to say it does mean something. And let's see what it does in fact mean. Let's just consider the following: 0.3333. Now we know what that means from the definition of decimals. What does this mean? This means 3/10 plus 3/100. Now normally you would write 100, but I'm writing as 10 raised to the power of 2 for a reason. You'll see. This is actually what decimals mean. So remember, I'm not figuring anything out here. This is literally from the definition of what a decimal is. It's by definition. Now let me do a little basic math work with fractions and factoring things out. I want to factor a 3 out, just because I kind of want the 3 out of the way so I don't have to pay attention to it. Now what would you have left? And I'm going to use the rules of exponents in here too. Right? 1/10 plus 1/10. Here, I'll write it like this. In fact, this might be a pretty good time to use a bracket here, huh? 1/10 raised to the power 1 plus dot, oh no, I don't dot dot dot. We know how many terms we have here. So 1/10 raised to the power 3 plus 1/10 raised to the power 4. Again, this means this because that's what decimals are. That's, I mean, again, literally the definition of what a decimal is. From here to here, I did some basic math, or hopefully it feels fairly basic at this point. But what are people trying to say when they write this down? They're trying to say that the series goes out to infinity. Now we have a formula to tell us what that means. And you know, I shouldn't have actually done this. What I actually should have done is erase this, because in a sense, well, that's true right there. But I don't want to assume the conclusion and create a circular proof of anything here. What if we go further and further and further out? Then what we're saying is 0.333, or we're actually going to declare or define this equals 3 times 1/10 to the power 1 plus 1/10 to the power 2 plus out to infinity. And now we have a formula for this. Except we almost do, but we don't. Remember this formula right here? This started with r raised to the power of 0. So what I'm going to do is an old math trick, and I call it the old add and subtract trick. This is just the kind of trick that used to drive me crazy, and maybe still does a little bit. I wanted a 1 to be here so I could use this formula. So I can't just arbitrarily add a 1. But if I add -1 and 1, I haven't done anything because that's 0. Well, now I've got a formula for this. For this right here, where r is 1/10. The common ratio is 1/10. So let me erase this right here. I don't need that. Yeah, I don't need that. Okay, don't need that. What does this mean? It means this. That's by definition. We did a little bit of math work and we got this. Now we have a formula we can employ. So let's see on the screen here. I'll get out of the way. I'll be getting out of the way here in a second. So this right here is equal to, I guess I don't need this anymore. This is equal to, so here, maybe put a little arrow up here like this. 3 times -1 plus, and now we've got the formula. And the formula says this is 1 over 1 plus 1/10. Sorry, minus. We can calculate all this. Let's just go ahead and do that. So this is equal to, hey, let's go ahead and do the distributive rule. Or we'll wait on the distributive rule. Okay, -3, -1 plus, what's down here? 1 minus 1/10? 9/10. Do the division, 10/9. -3, and then what's all this when we add this together? 1/9. And this is equal to -1/3. Except it's not -1/3 because it's a straight negative sign. Hey, had that been -1/3, I would have known I did something wrong, right? Don't know where that straight negative sign came from, but there it is, and that's 1/3. Now, what did I just show? I showed this 0.33 out to infinity. By definition, it means this. By some basic math, it means this. When you get to Calc 2, you'll see I'm glossing over a few things, but so if any of you remember this in the future, you may say, hey, he never mentioned that. Well, it's intermediate algebra. So equals this, which equals this by our formula, and then little basic math, this and this. So 0.333 repeating actually does mean 1/3. It really does. So it does mean something. And if you go back and review this, in a way, you're now justified. You're sort of qualified or justified in writing this 0.3333. Now, the book has some other examples of this, and I'm going to do another video. I'm going to be offline until Tuesday, but I'm going to do another video where maybe it's not quite as nice as it's just a single digit. What if it was 0.343434 or 347. So we have to just do something similar to this. And I'll show you how to do that on Tuesday. All right.